topic that's near and dear to my heart, nitinol and the supply chain and the manufacturing process. Just a very quick background on myself. I started playing with nitinol in 2001 at Memory Corporation in Connecticut. Did that for 11 years in a product development capacity, and then moved up to the melting facility up in upstate New York in 2013. So I've been on kind of the component side and now the melting side, about 50-50, enjoy both of it. There's a lot of activity and a lot of news around consolidation and concern about installed capacity, how nitinol is actually made. So we thought it would be a good idea to have this topic presented here at MD&M West. So jumping right into it, just give you an overview of what we want to talk about. We will detail our nitinol supply chain from raw materials to mill products being bar, coil, and plate. What it won't talk about is tubes, wires, sheets, components. That's all downstream. So we're talking about the front end, the feedstock that serves those particular product groups. And that's what we do in our facility in upstate New York. There are several other melters and in the market today. Some use alternate melt practices to what we use, but the conversion is largely the same. Most companies are using large aerospace partners like we are, and I will have some comments on that, including the next one. Aerospace partners are very busy. Again, I'll have some details later in the presentation, but that has made some tightness in the flow of material, and it is a short-term issue. So we'll go into the details on that. We'll talk about the installed capacity we have at Resonetics and our commitment to continue serving the entire community as an open source provider. So that is very important to us. So here's our facility in upstate New York. We recently expanded this. It's a little over 50,000 square feet. We were part of Special Metals. Special Metals is an aerospace producer, started in the 50s. Most of their product is aerospace grade Inconel 617, 718, things like that. It's actually that technology to melt that material is what we use to develop and confirm our current melt practice that we use today. And we actually melted nitinol for the U.S. Naval Ordnance Lab way back in 1966. So that's where nitinol gets its name. Nitinol is, the NITI is nickel titanium, and the NOL is Naval Ordnance Lab. Fast forward to 2008, Special Metals divested the business, just the shape memory division, because they had really no interest in that. They wanted to stay superalloys. So they did divest that, and they were acquired by a firm in outside of Milan, Italy, called Size Group. That was the same year they bought memory, so they did jump into nitinol quite strongly in 2008. And then they divested that business. It was bought by Resonetics last year. We went through a long process, and the deal closed in October last year. So I'm very happy to be part of the Resonetics group and to continue melting as an open source. One comment on this, in 2008, there was a huge amount of concern in the market because Size bought both the Special Metals division and memory at the same time. They were really worried about shutting off supply and restricting materials, jacking price up. So we spent a lot of time to reassure customers that that wasn't going to happen, that wasn't in our business model. And this week, that's pretty much all I've done is the same thing. So I've talked to many customers. If anybody wants to talk after this presentation, I'll be at booth 2511, and I can give you more information than what you'll hear here today. So what do we melt today? So we melt around 500,000 pounds per year. We supply basically everybody who's playing with nitinol. So we're supplying people who are making tubing, people who are making wire, sheet. We're also supplying our intercompany customers, so both Memory and Connecticut and California. We're also supplying Resonetics. About 2/3 of what we melt in-house goes outside, so it goes to these what we'll call third-party customers. So a lot of times we'll get questions from big OEMs, and Memory didn't make the tube, but we made the material. It went somewhere else to make the tube. It went somewhere else to make a component, but they'll call me and have questions on the cert. And we help just because we're certainly in this together. We all have the same group of end customers here, so it's in everybody's best interest to work together and help where we can. We do melt various formulations. I won't talk about these. I've circled the ones that typically go into medical applications, and really the only one that most people are interested in is the binary nickel titanium. That's the only one that is ASTM F2063 graded, and I do have a snapshot on the next slide. But those are the three big ones. 95 to 99%, depending on the mix is binary. So this is the spec that we melt to. This is not a technical presentation. I won't go into this line by line, but I just want to point out a couple things. So when you see on a drawing per ASTM F2063, if it's a final component, the spec doesn't apply to the component. If it's a tube, it doesn't apply to the tube. It only applies to very large product, between 5.5 millimeter and 94 millimeter. Hot rolled condition, and that's where they're speccing out the inclusion profile, the grain size, mechanical properties, chemical composition, things like that. So that's all done at this larger, what we'll call a mill product level. And that's kind of the scope of this talk here. Stipulates no intentional additions other than nickel and titanium, so we can't put something else in there. That's why our nickel, titanium, chrome, or cobalt, that's why they don't apply to F2063. That's also why a lot of customers are hesitant to put that in the body because of the FDA. They're concerned they'll have to do a lot of extra testing, biocompatibility. There's a lot of work to be done there. There's customers that use it successfully, but most everybody gravitates just towards the binary for that reason. So we'll get into the process of how we make the material. Again, I'll detail how we make it. There are other ways basically to melt it, but the conversion process is about the same. For us, our raw material supply, we take in raw nickel shot, and that's in the top right picture. We take in titanium sponge, the lower right. Those are our two materials. Those are the only materials that we charge the crucible with. We do not use revert, which is remelted material, so anything that we have to scrap through the process, if we downstream we condition, we peel the billets, we get a lot of turnings, or we have crops from the ends. We don't remelt that because every time we melt in a graphite crucible, we pick up carbon. Carbon is an impurity in the material, so all we would do is keep adding carbon to it. So we don't reuse any scrap. I'd like to point out these materials are not exotic. There are some melters using some really exotic, expensive materials, and we're not doing that. These are commercially available materials. We source them from long-term suppliers, and there's really no concern with getting these materials. So there's been a lot of talk about pricing fluctuation, especially with nickel and whatnot. So nickel is priced as a commodity, so it goes up and down with the LME, and on an annual basis we negotiate sponge pricing. We do have safety stock around 1 year. We are increasing that because we want to stay ahead of any increase in demand that might come our way. So we'll talk about the melting. So there's various melting technologies. This is a non-exhaustive list. I'll just read them off quickly. Vacuum induction melting, induction skull melting, electron beam. There's several different electron beam melting methods. I didn't know this until I got in the business and went and saw every one of these. So there's drip melting, cold hearth refining, there's floating zone, there's VAR, plasma, ESR, which is electroslag remelt, laser. There's some others here, but these are kind of the primary ones that you would use potentially for nitinol. For our material, almost everything we make, 95% is Vimbar. So we do a vacuum induction melt followed by a vacuum arc remelt. I have some slides that show you what those processes look like. In our Enduro, we're claiming that as proprietary today, so we don't divulge that. But our competitors, other people playing the space, they may use the same thing, the same technology. We call it the melt practice we do. Some are VAR only, multiple VAR. There's some various practices, and that's one thing that's very unique about nitinol. It's not all made the same. And I can look at a micrograph. We have to test it for that F2063 to look at inclusions. And when I look at our material versus someone else's, it's very clear there's a difference. And I'm not saying necessarily one is better than the other, but you can see a difference in the material just by how it's melted. Nitinol is not nitinol. So our production method, we start with a vacuum induction melt. We measure a charge out very precisely. So nitinol is very sensitive to the nickel titanium ratio. So we measure to essentially the last little piece of nickel shot. We measure out around a 200 kilogram charge, 420 pounds. All the materials go in a graphite crucible. The crucible was just a giant block of graphite that we have machined into a custom design for us. It lasts between 80 and 100 heats, and then we have to scrap it and put a new one in. Why do we use graphite? It has very good thermal shock resistance, and it's very resistant to degradation by the liquid nickel titanium. Liquid nickel titanium, the joke is it's the universal solvent. It will eat anything. If you try and use a crucible that's used for superalloys, an oxide, magnesia, alumina, zirconia, all you're going to end up with is nickel titanium oxygen. It will just suck up all that oxygen, and you might get 2 cycles to failure on your crucible. So over the years, we've really developed a grade of graphite to work for us. We do pick up carbon from it. It does dissolve a layer of the crucible, but to us, it's not a bad thing. We end up with a very fine distribution of inclusions. So the other advantage to doing this, or the main advantage to doing it, is everything is molten at the same time. Other melt practices, you might melt through a zone. If you have a direct VAR, revar, you compress a briquette of material, the same form of raw material I showed you earlier, and you apply current to it, and you melt, and you have a zone that's molten. So you have to remelt to try and get better homogeneity, whereas here, everything's molten at the same time. There's some currents that are in the crucible, which gets some mixing as well from the induction field. Once it's fully molten, we're happy. We hit a timer, we hold the material, we'll pour it off in a mold, and it freezes. So it takes about an hour from power on to power off to melt around 420 pounds of nitinol. This is a picture of our main production furnace. So this is what we call M1, and for reference, there's a man standing up here. So to me, it's a big furnace. If you've been to a steel mill, it's a toy. So it depends on your perspective. And it is done under vacuum. So there are sight ports on the machine, so the operator can watch this as he's pouring, as he's melting. He can monitor the melt. And we've been doing it the same exact way since 1990 with no changes. So that's when we first confirmed the VIM-VAR process, again, born out of the superalloy production. From there, we take a number of those castings out of the VIM, we weld them together, and we will put them into a VAR process. So now we're using a different type of crucible. It's a copper crucible, and it's water cooled. And we we have a stinger we put on the end of this electrode. It weighs about 2 tons, and we apply a lot of current to it, like 9,000 amps. And it will jump across to the copper stool plate, and it will drip off and superheat, and it will melt a new ingot from the bottom up. So we can control the solidification rate because we control how fast the ram comes down. We have load cells on the head, so we know how much weight is being lost. As we do this, we get 25 or 30 different parameters out of the furnace when we do it. So why are we doing this? A couple reasons. One, because we can take 9 small VIM ingots and make them into one, so we can process a bigger ingot with a larger lot size. The other reason is to control the structure. So we have a controlled solidification rate. We control, again, that ram speed, so we're allowing that liquid material to fill every void as it freezes from the bottom up. Again, there's different ways to do it. Some people, that's all they do is this one, and then they'll remelt, but you only get a molten area in a small zone. It's about so big, and it will just move on the way up. So again, different ways to make nitinol. On the left is what the product is. That's a full-size 2-ton, a little under 2-ton, 3,800 pound ingot. That's what we get from 9 VIMs that have been put together. Now we have a monolithic ingot. On the right is our in-house VAR. So we do have a small furnace for R&D, prototyping, small heat. So that can do 30 to 300 pounders, and we can do that in-house. Our commercial production, the larger scale on the left, is still done at Special Metals, our old parent company. So they're right across the parking lot from us. A lot of people that work for us worked there before, have run those furnaces. We have very close connections with them, so it's a easy interaction with them. Other than getting the throughput that we need, and I'll have some comments on that a little bit later here. Once we have the ingot, we need to convert it. It's tough to make a 3,800 pound product into a 25 micron wire or something like that. So we need to make it smaller. So we do this by forging. Most everybody who's working with large ingots do through forging. So either a two-jaw open die press, which is what you see in the picture. That is nitinol that's being forged in that picture. This is courtesy of Special Metals. And that's, I think, a 2,000 ton press. So this is huge capital equipment. This is something that we have to use these aerospace partners because we can't pay $500 million for a forge press. You can also do a gyratory forge where instead of having two jaws, the ingot will actually have manipulators that will move it back and forth as those two jaws come together. There's also gyratory forge where you've got 4 hammers in there, and they will move it back and forth as well, but it's a different way of doing it. GFM is a little more efficient. If you're talking really small ingots, you can extrude them or you can swage them. We've done it for small ingots. We do have the capability to go down to 30 pounders, but we don't do a lot of that. That's more of an R&D activity, and then we'll scale it up into the bigger furnaces, bigger ingot forms. So out of the forging operation, 1 ingot turns into 8 billets. So on this table here, this is 1 ingot's worth of material. So as we forge it, it gets longer and longer. This is what it looks like. It gets that kind of yellow-green, heavy nickel oxide on it. So we'll take that material, we'll crop the ends to remove these rag ends, we call them. We'll crop those off, make sure there's no pipe in it, and then we'll machine off around 1/4 inch off the diameter to pull off the hammer marks, pull off that heavy nickel oxide, and get a good conditioned surface that we can input into the next operation. From there, it goes to hot rolling. So most of our, by weight, most of our nitinol goes into wire form. The next would be bar, and bar would be feedstock for tubing products. And then a very small runner would be sheet, where we actually forge it into a rectangular section. But essentially, it's all the same process where you're heating the material, you're hot working it, so you're hot rolling the material. Nitinol does hot work very easily. Anybody who's used nitinol, made components, most people think it's terrible to work with because it is. It work hardens rapidly. It's really tough on tools. Hot works like butter. You need to have good control over your temperatures and your process, but it does hot work pretty easy. So the coil is produced, and a lot of bars produced on a very large mill. We did look at it, potentially insourcing this a number of years ago. At the time, the price tag was $80 to $100 million. It's 2.5 times probably that now to insource a hot rolling mill. Huge machine. It's not 1/4 mile long, but when I first saw it, it looked like it was. So you can get an idea of the size and scale of the type of equipment that it takes to do that. So come back to kind of summarize the process flow and the challenges that we have. So this is an important slide. So the ones in orange are our melting operation. Again, that's how we do it. That's not how everyone does it. Conversion, everyone's doing the same thing. So they're forging, they're peeling, they're hot rolling. A lot of us are using the same aerospace partners. So this first one is fully in-house. So we have an install capacity of around 1 million pounds, and we're using half of that today. So we have a lot of headroom. If we saw, the business going up strongly, we would be proactive and we would install a second furnace for that. But today we have plenty of capacity on that. It's also not labor intensive. We could do that. We could start melting at that rate next week. There's really no issue with that. It's not a labor heavy process. From there, the VAR, we are sole sourced. So I'm open about this. We are sole sourced with Special Metals on this. So we continue to work with them to try and get more and more product through as we've got this increase in demand for nitinol. And I'll have some comments on aerospace here later, which really applies to the next 3 blue boxes as well. So the conversion boxes, forging, peeling, and hot rolling, we have dual or triple sources for all of these. So we do have risk mitigation in place, but they're also very large aerospace providers. They're very busy. It's difficult to get their attention. We all fight the same thing. These mills do go down. There's breakdowns in these giant rolling mills, things like that. That's nothing new. That's always happened. The reason some of you might have been impacted or heard about that is because we just don't have enough material in the pipeline because we're throttled at VAR a little bit. And that's kind of seen in the industry as demand has really come up, is everybody's had some issues getting stuff through conversion. And normally you wouldn't necessarily see that because we would have the buffer in there with some additional material. So some comments on these aerospace partners and what's going on. So again, all of us are using major suppliers in the aerospace business. So if you watch the news, you look at aircraft orders, Airbus and Boeing, these out of these air shows, there's these massive airframe orders, Air India and others. There's a lot of increase in emerging markets in Africa, for example, push for more efficient planes. And it's really slowed down the conversion of our materials. So there's still there's still enough install capacity, but if they can push through their lucrative aircraft business, they're going to slow down working on this small volume material. And I should reinforce that this is Nitinol production. To us, it's huge. Try not to hit my mic. Got everybody's attention. Nitinol to us, 500,000 pounds is a lot to us, but to these types of industries, that's a shift, that's a week at best. So it's a very different size and scope of market. So that's where we're just trying to work with them, keep their attention. The invasion of Ukraine made the situation worse. Obviously, if you were sourcing titanium or any other aerospace materials from Russia, that's been a major issue. So there's been a big pivot, and that has made a lot of the converters that we use is really picked their demand up. Now we do see some softening. There's some people that I've spoken with that do see some reduction or again some softening in aircraft demand. There's a lot of materials in the pipeline. So really, as all these orders came in, everybody tried to get a piece of that business. So they really threw a lot of orders in the backlog, and we expect this to soften on its own, pretty soon. So what are we doing? We're going to continue working collaboratively with our aerospace partners to improve output during their time of high demand. So this is something, it's not new. I've been doing this for 11 years. It's sometimes one of the more frustrating parts of my job is, being able to control it on the front end, but then not being able to install a $500 million forge press, things like that. So it's nothing new working with these suppliers, and all other Nitinol producers are having the same issue. So we continue to educate them on patient impact. We have secured some extra melt capacity from Special Metals. They have agreed to, they've been at steady, what we need is steady state rate, but not enough to catch up, not enough to get ahead. So we did secure enough capacity to do that, and the situation should continue to improve. We expect by Q2 this issue has gone away, but that's the short term. Long term, we don't want to get in this position again. Plus, we all know the Nitinol market is growing. I expected about 4 people to this talk, being the last talk on a Thursday. So the fact there's quite a few people here means that there's quite some concern about capacity and continuity in the Nitinol production business here. So we are insourcing our own production VAR. So we did pull the trigger on that. So the equipment build is around 1 year, and then 6 months installation, validation, getting some materials into the pipeline. Even that takes time. Once we're validated, it takes quite a while to convert the materials. Typically from melt to market has historically always been about 6 months, so there is a lag. So this is not a quick fix for us, but this was something with our new parent company, Resonetics, coming in. They saw this as a gap that we had, and they see the increase in the demand, and we want to make sure that we can shore that up and serve customers better. So we are insourcing that. And between the first bullet point is the short term, the second long term, to rebuild those safety stock levels. So we want to put a lot of material at every bucket. We want to have material sitting waiting to forge. We want to have it sitting ready to peel all the way down through like we used to. So that's really what we want to do. Keep ordering materials on the front end and just populate all those stocking buckets along the way so that we can stay ahead and react a lot faster than we've been able to really since COVID. Lastly, just we want to reaffirm our commitment that we will remain open source. Again, just like in 2008 when Size bought the business from Special Metals, we will remain an open source. That's something we feel very strongly about. Our leadership feels strongly about. It's nothing that I had to sell them on. They're definitely interested in open source. It doesn't make any sense for us to shut everyone else out. So that's how we want to play in the market. And that's very important to us. This is a new tagline, part of something bigger. And to me, this means many things. So we're looking at patient impact. So we drive it down all the way down to employees, patient impact. During town hall meetings, patient videos, to make sure everyone understands. But part of something bigger also means it's not just us producing material for ourselves, it's producing for every step in the value chain. So we're going to continue to supply to providers, wire providers, sheet providers. At the end of the day, it's all the same end customer base, and we want to make sure everybody's happy and patients are what it is at the end. That's what the most important part. So that kind of concludes what I had here. I know I kind of hit you with a lot of information, so open it up for questions, and if anybody is not comfortable expressing a question here, I'll be at booth 2511 for, until it's empty. So. Any questions? Yeah. Yeah. I'm gonna go back here. Yeah. We're good? All right. Yeah, from melt to market, it's about 6 months. But so that's been our legacy melt to market. And even today, that is the melt to market, but just we're being throttled at that one point. So realistically, yes, it is longer than that. So we are, and then when you get down to, and what it does is stacks up with wire and tubing. So the biggest impact, has really been wire customers just because of the sheer volume of it. And then, we're trying to balance, we want to make sure everybody has the best access to material, and if it's a tube base, we try and do that, but it's just a smaller amount of material for tubes. So wire's been most impacted. That's why we currently have longer lead times on wire, and some of that is self-inflicted, is memory. We should have been extending our lead times. So we knew this situation was happening. Others that are making wire in the market did a good job as stuff started to throttle down a little bit. They kept pushing the lead times out, and we did a bad job. We waited until orders are ready to ship, and then we hit customers with, hey, it's going to be X, and that's something we're definitely changing. We need to fix our service level, and so we have made structural changes. And I didn't mention it. So I manage the melting facility and have for the last 11 years. I also now manage the 3 ex-memory sites, so New Hartford, Bethel, and California. So I do understand we put some customers in a bad position with that, and that's something we're working on. And that lead time should come down drastically. And as we get into Q2, things should get back to normal. That back to normal would be for wire. It's going to be whatever the typical lead time was, 6 to 8 weeks, depending on what it was. Yeah. Instead of 20. Yeah. Yep. No, it's a gap. We recognize it. We want to improve. Any other questions? Lead time for? Night tubes. Yeah, depending on what it is, it's going to be 8 weeks, sometimes quicker, depending on if we have an alloy ratio already in process. Yep. Any others? Okay, well, thanks very much for your time, and 2511, I'll be there if anybody wants to have a little detailed discussion.